Hello students, in this class we are going to discuss about stagger tuned amplifiers and stability of tuned amplifiers. So up to now we have discussed about single tuned amplifier and double tuned amplifiers. The single tuned amplifiers provides narrow bandwidth and greater frequency response, but the problem with the single tuned amplifier is because of narrow bandwidth we are not able to use those amplifiers for audio signals. That's why we went to double tune amplifiers. Double tuned amplifiers provides wider bandwidth, but they are difficult to align. The alignment is difficult. That's why we are going for stagger tuned amplifiers. Let us see need for stagger tuned amplifier. The double tuned amplifier gives greater 3 dB bandwidth, having steeper sides and flat top, but alignment of double tuned amplifiers is difficult. In order to overcome these problems, we are going for stagger tuned amplifier in which the two single tuned amplifiers are cascaded. The cascaded connection of single tuned amplifier is called stagger tuned amplifier. So let us see about stagger tuned amplifier. The stagger tuned circuit, two single tuned cascaded amplifiers having certain bandwidth were taken. In the stagger tuned amplifiers, we will take two or more single tuned amplifiers, and these single tuned amplifiers are cascaded. The resonant frequencies of two tuned circuits are so adjusted that they are separated by an amount equal to the bandwidth of each stage. If we are assuming we are taking the two single tuned amplifiers, those center frequencies or resonant frequencies are adjusted and they are separated by equal to the bandwidth of each stage. So that's why at the middle of these two frequency response, we will get the dip gain, just like in double tuned amplifiers. Since the resonant frequencies are displaced as staggered, they are known as stagger tuned circuit. Okay, as we are separating the resonant frequencies or displacing the resonant frequencies, this amplifier is named as stagger tuned amplifier. So, let us see the definition for stagger tuned amplifier. It is a circuit in which the two single tuned cascaded amplifiers having certain bandwidth are taken and their resonant frequencies are adjusted that they are separated by an amount equal to the bandwidth of each stage. Since the frequencies are displaced, it is called stagger tuned amplifier. This is the circuit for stagger tuned amplifier. So it is a combination of the two single tuned amplifiers. Up to this is one single tuned amplifier section, and this one is the second single tuned amplifier section. So we are giving the input AC signal to the stage 1 of the stagger tuned amplifier, and we are taking output from the second stage of the stagger tuned amplifier. The first stage output is taken via the coupling capacitor and then giving as input for the second stage. So these two stages are single tuned stages. So the tuning was done by this LC network which was connected in the collector circuit. So here Vs, Rs are the signal source and its source resistance. CCs are coupling capacitors. R1, R2, Re provides biasing, and CE is the emitter bypass capacitor. The LNC is the tuning tank circuit. VCC is the supply voltage, and we will take the output from the collector of second stage. In this graph, we can see the frequency response of individual stages and overall response of stagger tuned pair. This is the response for stage 1 and this one is the frequency response of second stage. Here F0 is the resonant frequency of our stagger tuned amplifier, and this is the resonant frequency of stage 2, and this is the resonant frequency of stage 1. The resonant frequency of the two single stages are separated by a distance delta 1 by 2 or delta by 2, where delta 1 is the bandwidth of each single stage amplifier. So as these two resonant frequencies are separated by delta 1 by 2 from the resonant frequency of stagger tuned amplifier, the distance between the two resonant frequencies of individual stages is equal to the delta 1, which is the bandwidth of individual stage. The half power 3 dB bandwidth of stagger tuned pair is root 2 times of bandwidth of individual single tuned stages. As we know that the delta 1 is the bandwidth of single tuned stage, in the overall response of stagger tuned amplifier, half power bandwidth is root 2 times more than the bandwidth of the individual stage. That's why we are getting more bandwidth that is useful for amplification of audio signals. So here F0 is the resonant frequency of stagger tuned amplifier, and these two frequencies are half power frequencies here and here. Let us compare the frequency response of the single tuned amplifier individual stages and the overall response of stagger tuned amplifier. So this is the response of the single tuned amplifier stage, and this is a one more single tuned amplifier stage response, and this curve is the overall stagger tuned amplifier response. The bandwidth of each stage is delta 1 or delta F, you can take, and the overall bandwidth of stagger tuned amplifier is root 2 times more than the individual bandwidth of single tuned amplifier stage. So one thing we can observe here is the single tuned stage is giving more amplification when compared with the stagger tuned signals. So the maximum gain that was provided by the each single tuned stage is 1, and the maximum gain provided stagger tuned is 0.5 only. It may be approximately half of the gain of individual single tuned stages, but the advantage in the stagger tuned amplifier is the more bandwidth, and alignment is also easy. The stagger tuned amplifiers can be extended to more stages. Suppose if you take 3-stage stagger tuned amplifier, the stage 1 is tuned to the frequency lower than the center frequency, and the third stage or last stage is tuned to the frequency higher than the center frequency, and the middle one or the second stage is tuned to the center frequency of our designing stagger tuned amplifier. So like that we can extend the stagger tuned amplifier to more number of stages. Let us quickly review about the stagger tuned amplifier. So why we are going for stagger tuned amplifier means, in order to eliminate the problem of alignment in double tuned amplifiers, we are going for stagger tuned amplifiers. The stagger tuned amplifier is a combination of two or more single tuned amplifiers, and these single tuned amplifiers are cascaded. The stage 1 output is given as an input for the second stage, and the second stage output may be given as input for the third stage, and so on. The center frequencies of these stages are separated from the stagger tuned amplifier resonant frequency, and the separation is equal to the bandwidth of each single tuned amplifier. So from the center frequency or resonant frequency of stagger tuned amplifier, to the center frequency of the single tuned amplifier is exactly half of the bandwidth of single tuned stage. If you see the overall response of stagger tuned amplifier, it is looking like a normal RC coupled amplifier, so which has wider bandwidth, which is root 2 times of the single tuned stage bandwidth. That is the advantage of stagger tuned amplifier. Let us quickly move to the analysis of stagger tuned circuit. We know that the relative gain of single tuned amplifier AV by AV resonance equal to 1 by 1 plus 2j Q effective into del. Here I am just assuming the 2Q effective del as X. That's why this relative gain can be equal to 1 by 1 plus Jx. Assuming my stagger tuned amplifier has the two single tuned amplifiers, so one stage is tuned to FR plus del and second stage is tuned to the FR minus del. As we know, del is the frequency deviation from the resonant frequency. So we know in the stagger tuned amplifiers, these resonant frequency of individual stages separated by some frequency del. That is shown here. Therefore, FR, the F0 can also be written as FR, the resonant frequency, FR minus del, and second stage is FR plus del. Like that we have taken here. Therefore, FR1, resonant frequency of one stage, and resonant frequency of second stage FR minus del. Therefore, AV by AV resonance for the stage 1 can be given as 1 by 1 plus J into X plus 1, and AV by AV resonant of the second stage is given as 1 by 1 plus J into X minus 1. These two equations are relative gains of individual single tone stages. So the overall gain of these two stages is a multiplication of individual stages. Therefore, AV by AV resonance of cascaded amplifier is the multiplication of stage 1 into the stage 2. So 1 by 1 plus J into X plus 1 into 1 by 1 plus J into X minus 1. So when we multiply the denominators, we will get 2 plus 2jx minus x square, and this can be splitted into two parameters, 2 minus x square plus 2jx. If you take modulus for the relative gain of our stagger tuned amplifier, it will become 1 by root of 2 minus x square whole square plus 2x square. So which is equal to, by applying a minus b whole square formula, so we will get this expression, and this can be simplified to 1 by root of 4 plus x power 4. And we know what is x. X is equal to 2q effective del. We assumed. Just we are replacing the x value with the 2q effective del, and x power 4 is represented here. So when we simplify the equation, it will become 2 root of 1 plus 4 q effective power 4 into del power 4. Okay, this is the relative gain of stagger tuned amplifier. By observing this equation, we can say the gain of stagger tuned amplifier is somewhat less when compared with the remaining single tuned amplifiers. So let us move to the comparison of the tuned amplifiers. We have mainly three types of tuned amplifiers. Those are single tuned, double tuned, and stagger tuned. Okay, so let us see the parameters. The number of tuned circuits. In single tuned circuit, we have only one tuned circuit. In double tuned, we have two. In stagger tuned, we have more than two. The Q factor of a single tuned amplifier is high, and the Q factor for the double tuned amplifier is also high, and the Q factor of a Stagger tuned amplifier is low because the bandwidth is more, and the selectivity is very high in single tuned amplifier circuits, and in double tuned it is moderate. The selectivity is very low in stagger tuned circuits. When compared with the bandwidth, the single tune provides narrow bandwidth or small bandwidth, and double tune provides moderate bandwidth. The stagger tune provides very high bandwidth when compared with the remaining two tuned circuits. The frequency response, we can see it is a very narrow band, and it is also called narrow band amplifier, and this is double tuned amplifier response having somewhat more bandwidth when compared with the single tone circuit, and this is a response of stagger tuned circuit which is having more bandwidth than the double tone circuit. If you see the applications, the single tone circuit can be used in RF amplifier stage in radio receivers, and the double tuned amplifier circuits are used as intermediate frequency amplifier stage in radio receivers, and the stagger tuned amplifier is used as a band pass filter. The next topic is stability of tuned amplifiers. The single tuned amplifiers are not stable at high frequencies. Why it is happening means because of interjunction capacitance between the base and collector. The interjunction capacitance is named as CBC, which lies in the junction of base and the collector. This capacitor is forming the feedback path from the output to the input, and it is providing the positive feedback. As it is providing the positive feedback, the amplifier will become as an oscillator. That is the problem at high frequencies. So why we are discussing about stability means at high frequencies, the interjunction capacitance between the base and collector is providing the positive feedback. That's why our circuits are not acting like amplifiers, and they are acting like oscillators. Okay, at high frequency, the reactance of the CBC is low. That's why it is providing feedback from the output to the input. As a result, the circuit becomes unstable. Because of that feedback, our circuit is becoming unstable, and it will stop working as an amplifier. It is working as a positive feedback. So that's why our circuit is acting like a oscillator instead of amplifier. In order to overcome this problem, we have different techniques. There are 4 techniques we are going to discuss here. One is Hazeltine neutralization, and Neutrodyne neutralization, and neutralization using coil, and rice neutralization. Let us see what is this neutralization first. The technique used for elimination of potential oscillations is called neutralization, or else it has one more definition. The effect of collector to base capacitance of transistor is neutralized by introducing a signal that cancels the signal coupled through collector base capacitance. This process is called neutralization. So what we are going to do in the neutralization is, we are going to provide one more feedback from the output to the input that should cancel this feedback effect, so that our circuit will become neutralized. How it got neutralized? Because this CBC is providing the positive feedback. That's why we are going to give the negative feedback, which is equal in the magnitude but opposite in sign. That's why this equal in magnitude and opposite in sign will get cancelled each other, and our circuit becomes neutralized. Okay, there is no effect of feedback, and our circuit will act like a amplifier again. So let us quickly move into the neutralization techniques. The first neutralization technique is Hazeltine neutralization technique. So in this technique, this is the circuit for that. Okay, in this circuit, the CN is connected between the bottom of the coil to the base of transistor, where Cn is the neutralizing capacitor. So as we discussed, feedback was provided at high frequencies because of the interjunction capacitance CBC. So this is providing the feedback, the positive feedback from the output to the input. In order to eliminate the effect of this CBC, we are going to use one neutralizing capacitor Cn, which is connected from the bottom of the coil to base of the transistor. By just adjusting the value of Cn, we can eliminate or we can neutralize the feedback effect. The Cn provides equal magnitude and opposite in sign of the feedback provided by the CBC at high frequencies. So this way we can neutralize the effect of feedback component in our tuned circuits. The second technique is Neutrodyne neutralization. This is a circuit for Neutrodyne neutralization. The working of Neutrodyne neutralization circuit is similar to the Hazeltine neutralization circuit, but only one difference is the Cn does not have the supply voltage across it. So we are connected the Cn to the secondary of the coil, so there is no supply voltage across it, and remaining working is similar to that. The third technique is neutralization using coil. So in this circuit we can observe that we are using one more extra coil which is called L, that is connected at the secondary of this tuned circuit, and we are assuming it is a multi-stage amplifier. The second stage base is connected here. In this circuit, L is a part of tuned circuit at the base of next stage is oriented for minimum coupling to other windings. The L is wounded on separate form and it is mounted at right angles to the coupled windings. Okay, so this is separately wounded in the form and it is right angles to the coupled windings. If the windings are polarized properly, the voltage across L due to the circulating current in the base will have proper phase to cancel the signal coupled to base to collector CBC capacitance. Okay, if these coils are right angles with the proper phase, then the voltage across the base will automatically equal in opposite magnitude of this feedback signal. Therefore, the circuit provides the neutralization. Here, the neutralization was provided by the L. That's why it is called as neutralization using coil. The last one is Rice neutralization. This is a circuit for Rice neutralization, and here one thing we can observe here is the center tapping was given to the ground terminal. The input side transformer center tap is given to the ground terminal and output transformer center tap is also given to the ground terminal, and Cn is connected between bottom of the coil to the bottom of the input transformer. This circuit uses a center tapped coil in the base circuit. This circuit provides signal voltages at the ends of tuned base coil are equal and out of phase, so that we can eliminate the effect of feedback from the CBC. So that this center tapped circuit will provide you equal magnitude signal as of the feedback signal provided by the CBC, and this signal is equal in magnitude but opposite with the phase of feedback signal from CBC. So in this way we are going to eliminate the effect of feedback at high frequencies in the tuned amplifiers. Therefore, what is the use of this neutralization? So as we know, the BJTs and FETs are unstable over some frequency range due to the feedback parameter like CBC. The feedback can be cancelled by additional feedback signal that is equal in amplitude and opposite in sign. Therefore, the transistor becomes unilateral from input to the output, not from output to the input, and it stops the oscillations. As I told, the feedback is positive. Our circuit will work like an oscillator instead of amplifier. So those oscillations will get stopped and we can achieve the neutralization using the 4 techniques. One is Hazeltine neutralization, and second one is Neutrodyne neutralization, and third one is neutralization using coil, and the last one is Rice neutralization. By using these 4 techniques, we can achieve the stability in tuned amplifiers.